I welcome back all to the course on Control System Engineering. In this video, we are going to learn the force voltage and force current analysis. And also, we are going to learn the electrical analogous of mechanical systems. Before going to learn about electrical analogous of mechanical systems, let me recall what we have discussed in the previous video. In previous video, we have discussed the various components of mechanical, translational, rotational systems and its mathematical expressions. Therefore, we have derived the transfer function of the given mechanical, translational and rotational systems. And also, we have learned the mathematical modeling of various electrical components along with its transfer function derivation. In this video, we will learn the analogous electrical model of mechanical systems. Before going to the topic, let us think why we need to convert the mechanical system into electrical systems. The reason is it is very easier to construct and analyze the electrical models compared to the mechanical models. Therefore, electrical analysis of other systems is of greater importance. Therefore, in this video, we will learn how to convert the given mechanical system into the equivalent electrical model. Now we'll start the electrical analogous of mechanical systems. If the mechanical system is a translational system, then the input of the system is force, but for the electrical system, the input may be voltage or current. Therefore, the electrical analysis of mechanical translation system is categorized into force voltage analysis and force current analysis. If the mechanical system is rotational, then electrical analysis of mechanical rotational systems is categorized into torque voltage analysis and torque current analysis. If it is force voltage analysis, the input of the electrical system is voltage and the response is current. For the force current analysis, the input of the electrical system is current and the response is voltage. We will see first the force voltage analysis and torque voltage analysis combinedly. These are the physical models of mechanical, translational and rotational, then electrical systems. And here the mathematical expression of translational system is F is equal to m into d square x by dt square plus b into dx by dt plus kx. For rotational system, it is t is equal to j into d square theta by dt square plus b into d theta by dt plus k theta. For electrical system, it is by KVL law, we have V is equal to L into d square q by dt square plus R into dq by dt plus 1 by c q, where q is the charge and it is equal to integral of I dt. First, we'll see only the force voltage analysis. Here, the mechanical translational system is having the input as force. It is analogous to the input applied to the electrical system voltage here. By the mathematical expressions given at the bottom of this slide, if we compare two expressions, the basic component values, mass, viscous friction coefficient B and spring constant K are analogous to the inductance L, resistance R and the inverse of capacitance 1 by C. So the mass element is analogous to the inductance, friction coefficient B is analogous to the resistance and spring constant K is analogous to the reciprocal of capacitance 1 by C. And the response displacement of the translational system is analogous to the charge flow in the electrical circuit. And the velocity, that is dx by dt term, is equal to dq by dt, that is equal to current in electrical system. Here the current is constant in all the components which are connected in series in electrical circuits. Similarly, the velocity acting on all the components connected in the mechanical translation system should be same. Therefore, the velocity of the translational system is analogous to the current passing through the series RLC circuit here. Now we'll see the torque voltage analogy. If the mechanical system is rotational system, then the mathematical expression, if you compare the input of the rotational system is torque, is analogous to the applied voltage in electrical system, that is voltage. And the basic components like momentum of inertia J, friction coefficient B, and torsional spring constant K are analogous to the inductance, resistance, and reciprocal of capacitance. And here, when the torque is applied on the rotational system, the output of the system is the angular displacement, which is analogous to the charge flow in the electrical circuit. And the angular velocity omega is analogous to the current. Now we'll move on to force current analogy and torque current analogy. Similar to the force current analogy, here also we have the mathematical expressions for translational, rotational systems and electrical systems. If we compare the mathematical expressions shown at the bottom of this slide, we'll have the force acting on the translational system is equal to the input current in electrical system I. And the basic elements like mass, friction coefficient, and spring constants are analogous to the capacitance C, reciprocal of resistance 1 by R, and reciprocal of inductance 1 by L. And the displacement of translational system X is analogous to the magnetic flux, where the voltage derivative of the magnetic flux is nothing but voltage. Therefore, the displacement in translation system is analogous to the magnetic flux. And the velocity acting on the translational system is equal to is analogous to the voltage across each component in the electrical system. Here the velocity, since the velocity is same acting on all the components of the translation system, the voltage across all the components in electrical system should be same. Now we'll move on to rotational systems to electrical systems. Similar to the force current analogy, we have torque current analogy, where the input of the system, rotational system, is torque, which is analogous to the input current of the electrical system. And the basic components like momentum of inertia J, rotational friction coefficient B, and torsional spring constant K are analogous to the capacitance C, reciprocal of resistance 1 by R, and reciprocal of inductance 1 by L. And the angular displacement of the rotational system is analogous to magnetic flux, and the angular velocity is analogous to the voltage. Now we will see the force voltage and force current analogy through a problem. how the given mechanical system will be converted to electrical model. In this problem, we have two objectives. First one is differential equations. Write the differential equations governing the mechanical system shown in the figure. And second object is draw the force voltage and force current electrical analogous circuits. And also we have to verify by writing mesh and nodal equations. Now we'll see the solution. This is the given mechanical model and it is translation mechanical system. And we know how to write the differential equations of the given mechanical translational system. In the previous videos, we have learned this. So we'll write the differential equation of the given mechanical model. As we know, the number of mass bodies present in the translation systems to be considered as the number of nodes. Therefore, we have two nodes here, M1 and M2. And we need to consider the displacements at each node as x1, x2 and so on. Here two mass elements are there, therefore we need to consider x1 and x2 are the displacements. Anyhow, these two are already given in the problem itself. Now we'll write the free body diagram at the node 1. Since we have four components, four opposing torques, four opposing forces acting on M1 and one applied force is acting on M1. Total we have 5 forces at node M1. F of t is the applied force and M1 is the opposing force on the M1 and FB1 is the opposing force due to viscous friction between the surface and M1. FB12 is the opposing force acting in between M1 and M2 due to the B12 dash part. FK1 is the opposing force due to K1 spring connected in between M1 and M2. Similarly, we'll draw the free body diagram at node 2. Here we have 4 components connected to M2 plus M2 acting on itself. Therefore, total 5 opposing forces acting at node 2. Fm2 is the opposing force due to the mass body itself, and Fb2 is the opposing force due to B2 dash pot. Fb12 is the opposing force due to B12 dash pot connected in between M1 and M2. Fk1 is the opposing force due to spring K1 connected in between M1 and M2. Fk2 is the opposing force acting on M2 due to K2 spring. Here there is no viscous friction acting in between surface and M2 mass body due to the M2 mass body is fixed. There is no viscous friction in between surface and the body M2. Now we'll write the differential equation at node 1 from free body diagram. Since we know that the opposing forces Fm1 is equal to m1 d square x1 by dt square, Fb1 is equal to b1 into dx1 by dt, Fb2 is equal to b12 into d by dt of x1 minus x2, because b12 is connected in between m1 and m2. The velocity is the differential velocity, and Fk1 is equal to K1 into differential displacement x1 minus x2. If you substitute all this opposing forces in force balance equation, that is Fm1 plus Fb1 plus Fb12 plus Fk1 is equal to f of t, we will get m1 d square x1 by dt square plus b1 dx1 by dt plus b12 d by dt of x1 minus x2 plus k1 into x1 minus x2 is equal to f of t. And say this is equation number 1. This is the first differential equation obtained. And from the second free body diagram, similarly, if we write the opposing forces in force balance equation, we will have m2 into d square x2 by dt square plus b2 into dx2 by dt plus k2 x2 plus b12 d by dt of x2 minus x1 plus k1 into x2 minus x1 is equal to 0. And say this is equation number 2. By rearranging the equation 1 and 2 to compare with the electrical model equations, substitute d square x by dt square is equal to dv by dt and dx by dt is equal to velocity v and x is equal to integral v dt. In equation 1, we will get like this: m1 dv1 by dt plus b1 v1 plus v12 into v1 minus v2 plus k1 integral v1 minus v2 of dt is equal to f of t. If you substitute in equation 2, we will get the equation like this: m2 into dv2 by dt plus v2 vt b2 vt plus k2 integral v2 dt plus b12 into v2 minus v1 plus k1 integral v2 minus v1 dt is equal to 0. These third and fourth equations are useful to convert the mechanical systems into electrical systems and to compare these equations with the equations obtained from the electrical systems. So first, now as of now, keep these equations aside. Now we'll convert the given mechanical translation system into electrical model by using equation number 3 and 4. Here, in this given mechanical translation system, we have two mass body elements. So in the electrical analogous model, there should be two loops. Since it is force voltage analogy, we should create two loops in the resultant electrical model. Since two mass body elements, we must have two loops in the electrical circuit. Say loop 1 and loop 2. Create two loops like this. Now will come one by one parameters. First, the input of the system is f of t. This is the source to the given translational model, and the analogous parameter in electrical circuit is voltage. Say it is E of t. Therefore, in the first loop, we have E of t source, voltage source. So connect a voltage source in the first loop, and it is not or nowhere come onto the second loop. It is connected alone in the first loop. And next component at first node is M1, and M1 analogous parameter in electrical is L1, inductance. And this M1 is not touching node 2, it is touching with loop 1 only, in node 1 only. Therefore, in electrical systems, we have inductor in loop 1, which is belongs to only loop 1. And connect this all these components common to loop 1 in series. And third component connected at node 1 in translation system is B1, and it is analogous to R1 resistor in the electrical model. Therefore, connect in series a resistor. Again, it is common to only loop 1. Next component in mechanical translation system is B12. And see, this B12 dash pot is common to M1 and M2, node 1 and node 2. Therefore, this mapping in electrical system, the component should be common to loop 1 and loop 2. The analogous component of B12 is R12 resistance. So connect a resistor which is common to both the loops. So connect like this. Next component in translation model is K1. This is again connected in between M1 and M2. Therefore, the analogous parameter 1 by C1, that is capacitor, should be common to both the loops. Therefore, first loop is finished. Now come to the second node at translational model. Here the first component is M2. The analogous parameter in electrical is L2, inductor. So connect an inductor which is belong to only loop 2. And second component in translation system is B2. The analogous parameter is R2 resistor. You connect a resistor for loop 2 in series with the inductor. And next component is a spring, which is only connected to M2. Therefore, the analogous parameter, the capacitor, is connected only to loop 2. So, already common components like K1, B12 between M1 and M2 are mapped to R12 and C1 in electrical model. So, no need to reconnect it again. So, complete the loop 2. This is your completed electrical model, which is analogous to the given translational model. Here, the velocity at node 1 is equivalent to the current passing through the first loop, and you can cross verify that the velocity acting at node 1 in translation system is common to all the components. Similar way, the current passing through all the components connected in loop 1, L1, R1 and E of t are same. Similarly, V2 is analogous to current I2 in loop 2. Therefore, the common components like K1, B12 connected in between M1 and M2 mass bodies have the differential velocity V1 and V2. Similarly here, in electrical circuits, the current passing through R1 and C1 components are having the differential current flow. Now we'll cross verify the electrical circuit obtained with differential equations. Till now we have converted the given mechanical translational system into the equivalent electrical model, but whether the given or obtained electrical circuit is correct or not, or it is analogous exactly to the mechanical model or not, to cross verify this, we'll write again the differential equations from the obtained electrical circuit and we'll cross verify with the differential equations obtained with the mechanical translational system. So take the obtained electrical model and write the loop equation in the first loop. First, you separate the circuit of first loop. This is the circuit. To write the loop equation, we need to know the voltages of each component. Therefore, write first the currents passing through each component, then it's easy to know the voltage across each component. Since the first one is E of t, voltage source, the voltage across this source is E of t only. The voltage across inductor L1 is L1 into di1 by dt, because the current flow through this inductor is I1. And the voltage across R1 is R1 into I1, R1 into I1, because the current passing through R1 is I1, and the voltage across R12 is R12 into I1 minus I2, because the current passing through R12 resistor is the differential current I1 minus I2. I1 is the first loop current and I2 is the second loop current. By the direction assumption, the current passing through R12 is I1 minus I2 for the first loop. Similar way, the voltage across C1 is 1 by C1 integral I1 minus I2 into dt. By the KVL law, the sum of these voltages is equal to 0. By the current direction, we have L1 di1 by dt plus R1 I1 plus R12 into I1 minus I2 plus 1 by C1 integral I1 minus I2 dt is equal to E of t. Since E of t has minus sign, after sending this to right hand side, we'll get is equal to E of t. Now we'll write the KVL equation for loop 2. So separate first the loop 2 circuit. This is the loop 2 circuit. Here we have 5 components. C1, voltage across capacitor C1 is 1 by C1 integral I2 minus I1 dt. Here I2 minus I1 is written due to the current direction. With respect to loop 2, I2 current is positive and I1 is taken in the reverse direction, therefore considered as negative. And the voltage across R12 is R12 into I2 minus I1. Voltage across L2 is L2 into di2 by dt. Voltage across R2 is R2 into I2. Voltage across C2 is 1 by C2 integral I2 dt. Here 1 by C is given, actually it is 1 by C2. Therefore, the equation is L2 into di2 by dt plus I2 R2 plus 1 by C2 integral I2 dt plus R12 into I2 minus I1 plus 1 by C2 integral I2 minus I1 dt is equal to 0. If we compare these two equations with the mechanical translation systems, we can know the exact electrical analogous parameters of mechanical system. Now let us move on to force current analysis. Similarly, the given mechanical translation system can be converted into the electrical analysis with respect to the current as input. In the force current analysis, we have to take two nodes, as we have two mass body elements in the given mechanical model. Whereas in the force voltage analysis, we have to consider number of loops is equal to the number of mass bodies present in the mechanical system. Whereas in force current analysis, we need to take the number of nodes as the number of mass body elements. So take two nodes, node 1 and node 2. Similar way, we'll take parameter by parameter and we'll convert into electrical analogous parameter. Here input is f of t, which is analogous to current in force current analysis electrical model. So take a current source, and this current source should be connected only to node 1. Second parameter is M1, analogous parameter is C1, so connect a capacitor in parallel with the current source. See, observe the difference. In force voltage analysis, we used to connect the components in series, but in force current analysis, we have to connect the components in parallel. Therefore, the node should be common. The third element is B1, analogous parameter is 1 by R1, so connect a resistor in parallel to this. And next component is B12 dash pot, analogous parameter is 1 by R12, connect this like this, resistor like this, because B12 in mechanical system is connected in between M1 and M2, that means in between node 1 and node 2. Similarly, in electrical system, we have to connect the resistor in between the two nodes, node 1 and node 2. So connect R12 in between node 1 and node 2. Next component in mechanical system is K1. The analogous parameter is 1 by L1, and here also K1 is connected in between M1 and M2. Connect an inductor in between node 1 and node 2 in electrical circuit also. And next, I think first node is completed. Now we'll move on to the second node. At the second node, we have the mass element M2, which the analogous parameter is C2. So connect a C2 in parallel to the circuit at node 2. And next element is dash pot B2. Analogous parameter in electrical is 1 by R2. So take a resistor and connect in parallel to this C2. Next and last component in mechanical system is K2 spring. Analogous parameter in electrical is 1 by L2. So take an inductor and connect in parallel to R2 and C2. Therefore, at node 2, all the components are connected. Now you can cross verify all the components which belongs to node 1 in mechanical system are exactly analogous in electrical system connected at node 1. Similar way at node 2, all the components connected in mechanical system are analogous to the components connected at node 2 in electrical system. And also the components connected in between M1 and M2 are analogous to the components connected in between node 1 and node 2 in electrical system. Now, after obtaining this electrical model, let us cross-verify by writing the differential equation. Here, we have two nodes, therefore we'll write the nodal equation by using KCL. Take a first node circuit, separate it. Now we'll write the KCL equation at each component, at each node, from each component connected to that node. Here at first node V1, we have 5 components connected. First one is the current source I of t. Second one is C1. Therefore, the current passing through C1 is C1 into dV1 by dt, because the voltage across C1 is V1 only. And the current passing through R1 resistor is V1 by R1. And current passing through R12 resistor is V1 minus V2 by R12. Here V1 minus V2 is written because the current direction is from V1 to V2. Therefore, the differential voltage takes place across R12 resistor. Similar way, the current passing through inductor L1 is 1 by L1 integral V1 minus V2 dt. Now we'll combine all these currents to get the differential equation. By the KCL, we have the sum of the incoming currents is equal to sum of the outgoing currents. Here the incoming current is only I of t, source current. It is equal to sum of the remaining currents. Therefore, C1 dV1 by dt plus 1 by R1 V1 plus 1 by R12 into V1 minus V2 plus 1 by L1 integral V1 minus V2 dt is equal to I of t. Similar way, we'll write the KCL equation at node 2. First we'll separate the circuit at node 2. Here also we have 5 components connected at node 2 V2. Similar way, if you write the differential equation, we will get at node 2 as C2 into dV2 by dt plus 1 by R2 V2 plus 1 by L2 integral V2 dt plus 1 by R12 into V2 minus V1 plus 1 by L1 integral V2 minus V1 dt is equal to 0. Now we have all these equations for different models. For the given mechanical translational model, we got the first two equations. After converting into electrical model using force voltage analogy, we got the equations given in the middle, and the last, using force current analogy, the mechanical system is converted into electrical model with these differential equations. If we compare all these equations from the mechanical analogy of electrical system, these all equations can be said correct. Like this way, we will convert a given non-electrical model into the electrical model. After converting into electrical model, it's very easy to construct and analyze. Therefore, it is required to convert non-electrical model to electrical model in many applications. I hope you understand the problem. So here I have given to practice problems for your sake. So please solve this, practice it, and cross-verify these answers so that you will get some idea on this. So I request you please practice these two problems and understand yourself how to convert a mechanical system into electrical model. So in this video, we have learned the electrical analogous of mechanical translational parameters, and we learned the electrical analogous of mechanical rotational parameters, and also we learned how to convert the given mechanical system to an electrical model using force voltage analogy, and also we learned how to convert the given mechanical model into electrical model using force current analogy. In the next video, we'll see some electrical systems examples like DC servo motor, AC servo motor, and synchros, and also we'll see how to derive the transfer function of those systems. Thank you.